All right, today our lesson is on 914, simplifying irrational square roots. Now, we've looked a lot at square roots recently, mostly in the context of rational square roots. We've looked at numbers like the square root of 100, which equals 10. We know that square root of something like 49 equals 7. And we know, obviously square root of 4, square root of 9, 25, all those good ones that come out to be whole numbers. These are what are called rational because they come out to be those whole numbers. So that's why these are called rational. Now today we're going to really be delving into the irrational realm of numbers. Something like square root of 2. We can't simplify the square root of 2, so it has to just stay in that way. We could find the decimal approximation, but technically the square root of 2 is what's called irrational. Another common one is the square root of 3, square root of 5, even something like the square root of 10. These all fall into the category of irrational because you cannot simplify them to become a whole number. When you put this into your calculator, you'll also find that this becomes an irrational number will always become a non-repeating, non-terminating value. So it never ends and it never repeats, even though on your calculator, it's going to tell you otherwise. It might tell you that it terminates after a certain number, but it really doesn't. All irrational numbers never end and never repeat the pattern. So that's what we're going to be really focusing on today. How do we deal with irrational numbers? Well, and particularly in regard to the quadratic formula. How can we rewrite the exact form of a root of a parabola using the quadratic formula? So let's go ahead and get started with our first example, and I'll talk you through it. Example number 1. We have y equals 3x squared minus 2x minus 3. So that's our first starting equation. We're obviously going to try and see if we can possibly factor this guy first, as we always do. And of course, I would have already looked to see, do they have a common value that I can extract? No. Do they have a negative a value? Nope, it's positive. So we are good to go with starting to do our factoring. I have a times c, which is negative 9x squared. And our b value goes on to the bottom, negative 2x. Are there any two numbers that can multiply to get negative 9, but that add to get negative 2? Nope. So therefore it is not, I shouldn't probably put an X, I should just put a line. This is not factorable. Now that doesn't mean it's not doable. It just means we can't put it into nice, neat factored form. So what we're going to do next is we're going to use our quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's go ahead and label our key components, or our necessary values. We have a equal to 3, b equals negative 2, and c equals negative 3. I usually just identify those three values by looking at my equation, 3, negative 2, and negative 3, in order to then use the quadratic formula. X is equal to negative, parentheses, negative 2, plus or minus the square root of, let's see, b squared, so we have negative 2, again, inside parentheses, quantity squared, b squared minus 4 times a times c. So a value is 3 in this case. Our c value is negative 3. All divided by 2 times a. So again, in this case, it would be 2 times 3. All right, let's go ahead and start simplifying this. We have a negative 2, which leaves us with a positive 2. Then we have that plus or minus sign. Negative 2 quantity squared, oops, sorry, got to draw my radical first. Negative 2 quantity squared is positive 4 minus 4 times, looks like negative 9, all divided by 6. When we go to simplify this next step, we're going to actually do the negative 4 times the negative 9 and just recopy everything else. 2 plus or minus square root of 4 And we have negative 4 times negative 9 right here. See that multiplication? PEMDAS tells us we have to do that multiplication before we do the adding or subtracting of the 4. So now we have 4 plus 36, because a negative times a negative is a positive, all divided by 6 still. All right, let's go ahead and simplify that radicand. So we have our final answer at this point for what we've been able to do of 2 plus or minus the radical of 40, all divided by 6. Now here's where our lesson becomes new, or this is where the new material begins. We need to simplify the square root of 40. So what I'm going to do is I'm going to draw a little box over here on this side of my paper. It's going to take about this much space to simplify the whole square root of 40. What we want to do is we want to figure out a way to make the square root of 40 be written into simpler form. So the first thing we always do with whatever the radicand is we need to write all the possible factors, or the numbers that multiply to get that number. So I'm always going to start with 1 times that number. Then I go up numerically. What's the next number after 1? 2. Does 2 go into 40? Yes, it does. 2 times 20 gets me 40. I would then keep going up. Does 3 go into 40? Nope. So I'm not going to do a factor with 3. How about 4? Yes. 4 times 10. After 4 comes the number 5. Does 5 go into 40? Yes, it does. 5 times 8. Again, these are pretty much all of our times tables, so we should have them memorized by now. I would then look and I would see, okay, where are my perfect squares within all of these, in this case, 4 options? I have 1 is a perfect square, and then I have 4 as the next perfect square. 4 is the highest perfect square that we have written here, because 5 and 8 are both not perfect squares. And so therefore, the 4 and the 10 is what I'm going to use to break down the square root of 40. The square root of 40 can be broken down into, oops, sorry, I grabbed the wrong color pen. The square root of 40 can be broken down into 4 times 10, but both of them still are required to be inside the radical because the 40 is inside the radical. But now we can take this and we can simplify it. We know that the square root of 4 is actually 2. It's a whole number 2. We can't simplify the square root of 10 because it's not a perfect square. So we keep it as 2 radical 10. And that's our final way of simplifying the whole square root of 40. Now we're going to do something in a second, so I am going to need this space down below to continue working. But for right now, let's take that and let's plug it back in to this equation over here. Over here we had x equals 2 plus or minus the radical of 40, but instead of putting the radical of 40, we're going to substitute in 2 times the radical of 10. X equals 2 plus or minus 2 times the radical of 10, all divided by 6. Now we notice here that all the numbers that are on the outside of the radical have something in common with each other. This one is a 2, this one's a 2, and this one is a 6, which means that we can simplify this down even further. Everything can be divided by 2 in order to simplify this. 2 divided by 2 is 1, 2 divided by 2 is 1, and 6 divided by 2 is 3. Which would be why, to find the exact roots of this problem, and I write this down because it is important for you to know there's a difference between the exact roots and what we're going to do with the decimal approximation in a quick second. But our final answer for the exact roots would be x equals 1 plus or minus the square root of 10. Notice how the radicand did not change. 10, 10. You don't simplify that part. Never the inside. All divided by 3. Now what we want to do next is, well, I should specify. If the problem asks us for the exact roots, bam, we are done. But if the problem asks us for, let's say, the graph of the problem or the decimal approximation, we have a few more steps to do. So I'm going to separate this, and this is again called the decimal approximation. We cannot ever find the exact decimal. Again, because this radical, square root of 10, is non-repeating and non-terminating. It never stops and it never repeats. It never forms a pattern. So we cannot ever find the exact decimal, unless, of course, it's a perfect square root. So what we would do is we would use that little handy-dandy paper that we already glued into our notebook, and we would come up with the decimal approximation of this value. What we would do is we would say, okay, the square root of 10 is the same as 2 times 5. So we have the square root of 10, which is the same as the square root of 2 times the square root of 5. Because obviously 2 times 5 is how we get 10. Which means that on this paper, we have the decimal approximation already given to us of square root of 2, which is 1.414, and the square root of 5, which is 2.236. So this is if we need to figure that out, just based on the roots right here. We could also utilize our graphing calculator, or just a regular old calculator is really all we need. We would take that 1.414, multiply it by 2.236, and we would end up with this value for the square root of 10. So now we actually could find the decimal approximation. We would say x equals 1 plus or minus this decimal, 3.161704, all divided by 3. Now what I would do is I would actually utilize my calculator, not necessarily graphing, but again, any kind of scientific calculator will do. I could do it on my iPhone calculator or something like that. So I would then do 1 plus 3.61704. I am going to press enter there. I either need to press enter and then do the dividing by 3, or from the beginning I would need to do use parentheses and do 1 plus 3.161704 end parentheses and divide that by 3. Notice how there's parentheses on the left and the right of the numerator before dividing by 3. If I don't do that, and I don't include parentheses, let's say I delete that, and I delete that, it's going to give me a number besides what is actually correct. Whoops, syntax here. Oh, because I added 2 decimals. Oh my gosh, I'm such a dork. Okay, so let's see it again with only 1 decimal this time. 1704 divided by 3. So what it's going to do is it's going to do PEMDAS. It's going to do the division first and then add 1 onto it. You'll notice that these two numbers are different. 1.387 is different than 2.0539, whatever. Okay, so that's why PEMDAS really does matter. So either use parentheses or do it step by step. Not a big deal either way. I kind of just prefer to do it this way, so I have control over the calculator, make sure I'm doing it right. So our first approximate value, and I'm going to use a squiggly tilde to do this decimal approximation, saying that I'm rounding. I have 1.387. I want to round to the hundredths place, so I look at the 7 tells the 8 to bump up. So my first root is approximately 1.39. Again, 7 tells the 8, bump up. My second value is 1 minus, or 1 take away, 3.161704. Enter, divide by 3, and we get our second root, which is negative 0.720. 0 tells the 2 to stay the same, and that's how we would get our 2 decimal approximations for this one problem. Again, it depends on what the question is asking for. Is it asking for the exact roots? Then we got to have it in radical form. If it's asking for the decimal approximation, or if it's asking us to graph, we definitely need to find the decimal approximation, because that will tell us where the actual values approximately cross over the x-axis to find those x-intercepts and the roots, which are the same thing. Hopefully that all made sense, and go ahead and give it a go for the practice problems on the slideshow.